Welcome back, AP Chemistry students, to Unit 8, Acid-Base Chemistry. Today we will be talking about Unit 8.3, the pH scale. Going through biology in your 9th or 10th grade year, or even in 8th grade, you learned what the pH scale was. The pH scale tells you if something is an acid or a base, where anything from 0 to 7 is considered an acid, and a pH anything above 7, and you probably were taught up to 14, is considered a base. But you might not know, where do these numbers come from? What's special about the numbers of 7 and 14? And for that, welcome to AP Chemistry, the pH scale. So the pH scale is based off of that equilibrium we started this unit talking about, how water can self-ionize. Two water molecules can collide with one another to produce hydronium and the hydroxide ion. Hydronium is able to break down metals. Hydroxide is able to neutralize that effect. The two together set up an equilibrium. But this reaction is heavily favored towards the formation of water. Only about 1 in every 10 trillion water molecules actually undergo this reaction. Since only about 1 in every 10 million water molecules undergo this reaction, if we take the concentration of our hydronium times the concentration of our hydroxides, that means that water has a self-ionization constant of 1 times 10 to the negative 14th at standard conditions. Standard conditions would be the conditions at which we usually conduct an experiment, which is about 25 degrees Celsius. So as long as you're at 25 degrees Celsius, water has a self-ionization constant of 1 times 10 to the negative 14th. And right there, you might start drawing some ideas about where that 7 or 14 came from. When it comes to pure water, at 25 degrees Celsius, if you have pure water, that means you have an equal amount of hydroxide and hydronium. That means the water is neutral, and those values are the same. And as long as it's pure water at 25 degrees Celsius, it's 1 in every 10 million water molecules. However, if you add something to this reaction that adds more hydroxide or more hydrogen, therefore more hydronium, you'll produce a solution that's either more basic or more acidic. Adding something with more hydroxide will make a basic or alkaline solution, while adding something that adds hydronium would make an acidic solution. It is a true equilibrium, and since we know that, we can figure some things out based off of that knowledge. If at 60 degrees Kw is 1 times 10 to the negative 13th, is the reaction endo or exothermic? Now this is example 5 in your packet. Honestly, I would do example 5b first, because it will tell us which way it goes. Alright, so Kw at 60 degrees, they say, is 1 times 10 to the negative 13th. Now that has to equal the concentration of the hydroxide and the hydronium ion. Since we know this value, these would both change by an equal amount, right? So x and x, based off of our Rice table, right, seen above. So doesn't 1 times 10 to the negative 13th have to equal x squared? So if we take the square root of both sides, we get 1 times 10 to the negative 6/2. Now true, that is not a good answer, but it does allow me to look at this first question. Is this an endo or exothermic reaction? At 60 degrees, we found that the concentration of hydrogen ions was 1 times 10 to the negative 6/2. At standard conditions, at 25 degrees, the concentration of hydrogen ions, I just said, was 1 times 10 to the negative 7th. So what happened? The concentration of hydrogen ions went up, right? Negative 6 is a bigger number than negative 7. That means at a higher temperature, we favored the production of products. That has to mean that at a higher temperature, that temperature must be used by those water molecules to make more hydronium and more hydroxide. So this is an endothermic reaction for this first answer. If we wanted an actual value here, if this was a free response, please do not write 1 times 10 to the negative 6 as an answer, 6/2 as an answer. So we'll grab a calculator and get an actual concentration, which is 3.16 times 10 to the minus 7th. However, as long as we are at 25 degrees, then our equilibrium position for the self-ionization of water is a constant. So if I know the concentration of hydroxide, I can determine the concentration of hydronium by simple algebra, because 1 times 10 to the negative 14th has to equal the hydroxide times the hydronium concentration. So in exercise 6, we are given either hydroxide or hydronium concentration, and we are asked to determine the opposite and whether the solution is acidic, basic, or neutral. Remember that the self-ionization constant of water has to equal the concentration of the hydronium times the concentration of the hydroxide. So 1 times 10 to the negative 14th has to equal the concentration of hydrogen times the concentration of hydroxide. So for this first one, since we are given hydroxide, we can solve for the concentration of hydrogen by dividing by the concentration of hydroxide on both sides. So 1 times 10 to the negative 14th divided by 1 times 10 to the negative 5th has to equal the concentration of our hydronium. The concentration of our hydrogen ion is 1 times 10 to the negative 9th. In order to determine if this is an acid or a base, simply compare the two. Negative 5 is larger than negative 9. Since this has more hydroxide, this is an alkaline solution. Our equilibrium, our self-ionization of water has to equal the concentration of hydrogen ions times the concentration of hydroxide ions. Again, since we have the concentration of hydroxide ions, we can divide by hydroxide on both sides to determine the concentration of hydrogen. So 1 times 10 to the negative 14th divided by 1 times 10 to the minus 7th will give us the concentration of hydrogen ions, which comes out to be 1 times 10 to the minus 7th. Comparing the two will tell us if this is an acid or a base. 1 times 10 to the negative 7th is the same as 1 times 10 to the negative 7th. Since these are the same, we are in a neutral solution. This is pure water. Lastly, if I have 10 molar hydrogen ions, I want to find the concentration of hydroxide. Since our equilibrium position for the self-ionization of water has to equal the concentration of hydrogen times the concentration of hydroxide, if I divide by the concentration of hydrogen on both sides, I can get my answer. So 1 times 10 to the minus 14th divided by 10 will give me the concentration of hydroxides, which comes out to be 1 times 10 to the minus 15th molar. Comparing the two will tell me if I have an acid or a base. 10 is substantially bigger than 1 times 10 to the negative 15th, so this is an acidic solution. Now, as you can imagine, working with all of these decimal places and scientific notation is a nightmare to do. And if we wanted to discuss these values, you wouldn't want to say that the concentration of hydroxide is 1 for every 10,000 water molecules. That can get really confusing very quickly. So, we developed the pH scale based off of logarithms. Logs are a way of working with very large or very small numbers simply. And so when we do pH, we focus on the negative log of some value. Like, for example, pH is the negative log of the concentration of hydrogen. Or pOH is the negative log of the concentration of hydroxide. And you can even do other things like pKa, which would be the negative log of the Ka. All logs have some base, and for this course, having Algebra 1 being a prerequisite, you simply need to know logs base 10. Meaning, a log is simply going to answer the question, what would you have to raise 10 to get some number? So, if I wanted to take the log of 100, that's simply saying, what number do I have to raise 10 to end up with 100? You're smart, you're pretty, gosh darn people like you. You know that in order to get 10 to 100, you'd have to square it. 10 raised to the second is 100. Or, if I want to take the log of 0.1, that's asking, what number would I have to raise 10 to end up with 0.1? Again, smart, pretty, gosh darn people like you. You'd have to raise 10 to the negative first. So logs can be used to deal with very large or very small numbers. In this unit, we are going to focus on the small number aspect. What number do you have to raise 10 to get some small value? And if it's a free response, use your calculator. You can do logs in your calculator, do them that way. However, on the multiple choice portion of the test, you do not get a calculator. So you need to be able to do some mental logs in your head. Most of the time, those logs will be fairly simple. So like if we were to take the log of some of the people in the school's age, some of them you could do right out the gate, right? Like if someone at our school was 1 year old, it's a terrible example, but you're smart, you're pretty, gosh darn people like you, what would I have to raise 10 to get 1? Anything raised to the 0 power is 1, so the log of 1 is 0. Or if I have someone at the school who's 10, in order to get, what would I have to raise 10 to in order to get 10? I'd have to raise it to the first. Or if we take the log of your principal's age, right? Your principal's been at the school for 100 years. So what is the log of your principal's age? What would I have to raise 10 to get 100? Again, the answer's 2. Fairly straightforward. But chances are there's no one who's 100 or even 10 at your high school. Most people have some ages that vary quite drastically. So how do those work? Well, let's think about it. If someone was 5, right, what would I have to raise 10 to get 5? Now, chances are you don't know, because to be honest, I don't know. But I could tell you what it's between. This number has to be between 0 and 1, right? Because the number 5 is between the ages of 1 and 10, right? So it's got to be between these two, but it's never going to actually be either of them. It's got a limit. The highest limit is a 1, the lowest limit is 0. So what does it actually turn out being? The log of 5 is 0.7. Okay, well that fits. 0.7 fits in to that value. Now, is it perfectly between the two? No, because this is a limit. So it's never going to be that nice and pretty. But what would the next one be? Let's say we took the log of your age. You're probably about 17. So what number would I have to raise 10 to get 17? Well, plug it in your calculator, and you'll see that it's 1.23. Again, we expect a value between 1 and 2, and 1.23 meets that. If we took the log of, say, your parents' age of 31, again, we could probably say it's probably going to be between 1 and 2, but it's got to be higher than 1.23, right? Higher than 1.23 because 1.23 was 17, so it's 1.5. So what is the upper and lower limit of, say, my age, 50? What is the log of 50? Well, the lower limit is going to be 1.5. The upper limit has got to be 2, because I'm not 100 yet. And sure enough, the log of my age is 1.7, right? Because that's how halfway between these two worked. So halfway between these two, 1.7, 0.7, sounds good. Now, with this idea that you have an upper and a lower limit as you move from one decimal place to the next, let's see if we can convert this to pH, where we'll be working with very small numbers. So remember, as you approach the next power of 10, your coefficient is going to increase. This value is going to get bigger as we approach the next power of 10. All right, so when we talk about concentration, keep in mind concentrations generally are small. So if we have a concentration of hydrogen ions of 0.001, well, what number would I have to raise 10 to get 0.001? The minus 3. I have to move the decimal place 3 spaces, right? Okay. Or if I had 0.02, I'd have to raise 10 to the second. So this is a -2, this is a -3. All right. So far, so good. So, what would be the log of 0.002? Which way are we moving? This number is getting bigger, and eventually if it got to 9 and then rolled over, this value would increase. Now what is that? That's the -1, right? 10 to the -1. So our limit here for what this number has to be between is a -2 and a -1, right? So this value has to be somewhere between the two. So when we plug it into our calculator, we get a -1.7. Okay. What about 0.03? Again, this value is getting bigger, so what does it have to get closer to? It's going to have to get closer to a -1. So we type in our calculator, or we think about it, it's got to be closer to -1 than a -1.7. So it comes out to be a -1.5. And each time we move closer to the next step up, it's going to get closer because these are negative values. All right? So unlike before when we talked about them getting bigger, here we're getting negative values. So remember, bigger is smaller. That made sense in my head when I said it. So what value does this one have to be? Well, it's got to be closer to 1 than -3. So it's probably like a -2 something. And sure enough, if you type it in your calculator, get a negative 2.3. You do not have very many multiple choice questions on the AP exam where you will have to do hard mental math like this. You will have to pick it out of a crowd, and you should expect easy math. More often than not, they'll give you concentrations that are easy multiples of 10. However, if you don't get that, you may have to pick out of a crowd which of these matches best to your pH. pH and pOH are not all that difficult. They kind of run opposite one another because they are related by that equilibrium, the self-ionization of water, which is the concentration of hydrogen times the concentration of hydroxides. And as long as you are at 25 degrees, as long as you are at standard conditions, that means that together they have to equal 10 to the minus 14th. Or, in terms of pKw, the pKw be the negative log of 10 to the minus 14th, or just 14. So pH plus pOH has to always equal 14. Now, that's where those numbers come from. That's your history lesson. If you don't memorize that, it's not the end of the world, because it is on your formula sheet right here are all the pH, pOH, pKw, KW things you could possibly want to know about. And as it says right here, pH plus pOH has to equal 14. This formula will adjust at the end of the unit, so if this is on your formula sheet, if you're taking the take-home version of the test, we will be scratching through this Henderson-Hasselbalch equation, but that is a story for later. So pH plus pOH has to always equal 14, like it says on your formula sheet. Please remember that P anything is the negative log of that value. If we have the pH, however, we can go back to the concentration by undoing the log. So we'll raise 10 to the negative pH to get the concentration of hydrogen. Or if we want the concentration of hydroxide, we'll raise 10 to the negative pOH. This also means, though, that the pKw has to equal a acid's Ka times its Kb. So these formulas, again, on your formula sheet, are great things to use in order to get one value if you know the other. So let's learn by doing in exercise 7 in your packet. We talk about how blood has a pH of 7.4. Calculate the pOH of blood, its concentration of hydrogen, and the concentration of hydroxide. So remember that on our formula sheet, we know that pOH plus pH has to equal 14. So if we have a pH of 7, the pH plus pOH will always equal 14. So if I want the pOH, I can do 14 minus the pH, which would be 14 minus 7.41, to give me the pOH of blood, which is 6.59. pH and pOH are naked numbers, so we don't have units, so this is our answer for this first one, now that we have the pOH. With the pH and the pOH, we can calculate our concentrations. Our concentrations are 10 raised to the negative of that value. So the concentration of hydrogen is 10 raised to the negative pH, while the concentration of hydroxide is going to be 10 raised to the negative pOH. Concentration of hydrogen is going to equal 10 to the negative pH, which we were given as 7. So the concentration of the hydronium ion is 3.89 times 10 to the negative 8th molar. The concentration of hydroxide equally is easy to determine. It'll simply be 10 to the negative pOH, so 10 to the negative 6.59. gives us a concentration of hydroxide ion of 2.57 times 10 to the negative 7th molar. When dealing with a strong acid or a strong base, when a strong acid or base is utilized, they completely dissociate. So, for example, for exercise 8, when nitric acid dissociates, every single nitric acid molecule will give us a hydronium and a nitrate anion. That's its dissociation, and yes, it does set up a small equilibrium, but that equilibrium is so heavily favored that we are going to say effectively that this concentration is the concentration of each of these ions. Because for every one nitric acid that dissociates, I get one hydrogen and one hydronium. So if a tenth of one dissociates, I get a tenth of a mole of hydrogen and a tenth of a mole of the nitrate ion. In which case, if I want to determine the pH equals the negative log of the concentration of the hydronium ion. So pH equals the negative log of the concentration of hydrogen, which again, since this is a strong acid, is the same as the concentration of the acid. So the pH of 0.1 molar nitric acid is 1. Hydrochloric acid also is going to dissociate completely. So when it dissociates, I get a hydrogen and a chloride ion. The concentration is going to be a 1-to-1 ratio. For every one hydrochloric acid that dissociates, I get one hydrogen ion and one chloride ion. So if 1 times 10 to the negative 10th dissociates, I'll have 1 times 10 to the negative 10th molar of each of the ions. And again, the pH is simply the negative log of the concentration of hydrogen ions. So the negative log of 1 times 10 to the negative 10. So the pH is 10. When dealing with a strong base, you'll end up calculating the pOH and then going from there. Sodium hydroxide is a strong base. For every sodium hydroxide that dissociates, I'll get a sodium and a hydroxide in a 1-to-1 ratio. So if one sodium hydroxide separates, I'd end up with one sodium and one hydroxide. But if 5 times 10 to the minus second dissociate, I would end up with 5 times 10 to the minus second molar concentrations of each ion. And I could find the pOH going a long way around. However, I like easy math. pOH plus pH has to equal 14. If I want the pH, if I determine the pOH first, simple subtraction will give me the pH. So the negative log of the concentration of hydroxide will tell me what the pOH is. So the negative log of 5 times 10 to the minus second gives me a pOH of 1.3. So 14 minus 1.3 will tell me the pH, which we come up as 12.7. With that being said, you can do page 17 in your packet. Page 17 deals exclusively with determining the pH and pOH of strong acids and bases. Be on the lookout for something polyprotic like sulfuric acid. You need to double the concentration. And while that's a little simplified version, we will talk more about sulfuric acid later. Same with a strong group 2 base. You would need to double the concentration of the hydroxide ion. It's a fairly straightforward worksheet. Pause the video and complete page 17. When dealing with a weak acid and base, we set up an equilibrium, where we are given the equilibrium position, and we can determine the concentration, the concentration of hydrogen ions, which is just a reactant there, so we could determine this value and determine the pH from that, or we'll be given the pH, which we will turn into the concentration in order to determine what the equilibrium position is. We'll do the same with bases. A weak acid and a weak base will set up an equilibrium. We will either determine the pH from our Rice tables, or we will determine the Ka given the pH. It sounds more complicated than it actually is, so let's just get straight to it. Example 10 in your packet has us calculate the pH of 10 molar acetic acid, and they give us a Ka of 1 times 10 to the negative fifth. So we need to determine the pH of 10 molar acetic acid. If we set up our Rice table, when we put our 10 molar acetic acid in solution, we would start with 10 molar acetic acid, no hydrogen or acetate ions in solution. And they will change by some amount, where the acetic acid will decrease by some amount, the acetate and hydrogen ions will increase by that value. So at equilibrium, we have 10.1 minus the change, and simply the change. In order to determine the pH, we need to know what is that change. We need to know what is our equilibrium value for our concentration of hydrogen. So we are given a Ka. Ka is going to be the concentration of the hydrogen ion times the concentration of the acetate ion over the initial concentration of the acid. So plugging in some values here, we have x times x over 10.1 minus x has to equal 1.8 times 10 to the minus fifth. And once again, we have landed in that quadratic quagmire that we talked about in the last unit. You have x squared over an expression containing that x. And just like in the last unit, this value of x, the largest it could possibly be is this Ka. If everything else had canceled out, x could only be 1 times 10 to the minus fifth. This is what that value would be. That's the maximum limit of what x could be. If I add this value or subtract this value from 10, does that make any difference? No, because 10 is so massive that this highest limit possible for x is negligible. So once again, when we land with quadratic equations in our equilibrium expression, you can neglect the x of the original concentration as long as 100 times your equilibrium position is less than the initial concentration. The short answer is, remember, the AP exam does not favor students that have a quadratic solving calculator, so the short answer is you will always be able to neglect this x in the denominator. You just have to explicitly say, I am neglecting this x. In which case, this problem becomes much simpler. X squared over 10.1 has to equal 1 times 10 to the minus fifth. So if I multiply by 10 on both sides, it goes away. So 1.8 times 10 to the minus fifth times 10 is 1.81 times 10 to the minus fourth equals x squared. Take the square root of both sides. To determine the value of x is 0.013 molar. Now that's the concentration of hydrogen, and while it's not important for right now, you might want to get in the habit. It's also the concentration of the acetate ion. Unfortunately, that is not what the question wants. The question wants the pH of this solution. So remember, pH is the negative log of the concentration of the hydronium. So the negative log of 0.0135 is our answer. 1.87 is our pH. Let's do it again. Hypochlorite is the active ingredient in bleach. It's also what's used in your swimming pool. Now, the hypochlorite ion does set up an acid-base equilibrium. It's a very, very weak acid. It has a Ka of 3 times 10 to the negative 8th. If you put 0.1 molar hypochlorous acid into your swimming pool, what is its pH? So, hypochlorous acid will set up an equilibrium to form hydronium and the hypochlorite ion. So initially, if I start with 0.1 molar hypochlorous acid in my solution, I'll have no hydronium or hypochlorite. However, it's going to decrease by some value, and the hydrogen and hypochlorite ion are going to increase by that value. So at equilibrium, we'll have 0.1 minus x, x, and x. Now Ka has to equal the concentration of the hydrogen ion times the hypochlorite ion over the concentration of the initial acid. Plugging in our rice table, we get x times x over 0.1 minus x. Has to equal 3.5 times 10 to the minus 8th. Even if x was the value of Ka, 0.1 minus 0.000003 does not cause a measurable difference. So we are going to neglect this denominator here. So we end up with x squared over 0.1 equals 3.5 times 10 to the minus 8th. So if we multiply by 0.1 on both sides, we get x squared equals 3.5 times 10 to the minus 9th. Take the square root of both sides will give us that x equals 5.92 times 10 to the minus 5th molar. That's the concentration of our hypochlorite ion as well as hydrogen. We can use that concentration to determine the pH. pH is the negative log of the concentration of the hydronium ion, so the negative log of our answer of 5.92 times 10 to the minus 5th. And we get a pH of 4.23. Example 12 has us go the other way around. We are given a base. I know this because I'm given a Kb. So I need to figure out what is the pH of this base. Now, there are a couple different ways to go about doing this. Personally, I am going to determine, just like before, if I'm given a base, I'm going to determine pOH and simply subtract that from 14. Because 14 minus pOH will always give me the pH. So I'm going to determine my pOH, and the meaning I need to figure out how much hydroxide this substance makes when it sets up its equilibrium. Now, if you don't know the formula for methylamine, don't panic. Just assign it a formula. You know that it's a base, so just be like, it's a base, there you go, who cares? It's going to set up a base, forming some cation and the hydroxide anion. And so, with methylamine setting up that equilibrium, I can determine my concentration of hydroxide and then subtract that from 14. So, initially, I'd have 1 molar, none, and none. This will decrease by some value. This will increase by that value. in which case at equilibrium I'd have 1 minus x and x. Now Kb has to equal the concentration of the hydroxide ion times the concentration of whatever cation methylamine makes over the initial concentration of methylamine. So 4.38 has to equal x times x over 1 minus x. And again, this value is so infinitesimally small that it's not going to make a difference. I can neglect it. So I get 4.38 times 10 to the minus fourth has to equal x squared over 1, multiply by 1 on both sides. X squared equals 4.38 times 10 to the minus fourth, square root of both sides will tell me that the concentration of hydroxide is 0.0209 molar. It's also the concentration of whatever methylamine makes. If you're playing the home version of this game, methylamine is an amine group attached to a methyl. They'll pull off a hydrogen from it, making hydrogenated methylamine and the hydroxide ion. So the hydrogenated methylamine cation has a concentration of 0.02. But that's not important because the question wants to know what is the pH. In order to do that, we're going to do 14 minus the pOH. The pOH we can calculate now as the negative log of the concentration of hydroxyl. So the negative log of 0.02 tells us that the pOH is 1.68. So pH equals 14 minus 1.68. So the pH is 12.3. For those of you in another AP class, there is another way to go about doing this, where you do Kw equals Ka times Kb. Use Ka to write this reaction in reverse, showing how it forms an acid. You could have gone about doing that as well. However, for me, for my course, why work hard when you can work smart? If I'm giving Kb, make it be a base. If I'm giving Ka, make it be an acid. Don't work harder than you have to. So with exercise 13, we have a similar problem. You can substitute ammonia and just be like, ammonia is going to form some cation and a hydroxide. I know this because it's a base. Or you might remember from the beginning of this unit that ammonia reacts with water to produce ammonium and hydroxide. Whether you write the equation this way or this way, the setup is going to be the same. Initially, I would have 15 molar ammonia and an infinite supply of water. Keep in mind, water is a pure liquid, so we do not include it. I'd have no ammonium and no hydroxide. It will change by decreasing by some value and increasing in products. So at equilibrium, I would have 15 minus x, and I'd have x and x. Now that Kb has to equal the concentration of the ammonium times the concentration of the hydroxide over the concentration of the ammonia. We don't include the water because it's a pure substance. So Kb of 1.8 times 10 to the minus fifth has to equal x squared over 15 minus x. Again, this x can only be but so big. So if we were to take 1 times 10 to the minus fifth and subtract it from 15, we would still have 15. So this is a neglectable value. So 1 times 10 to the minus fifth equals x squared over 15. Multiply by 15 on both sides. to get that x squared has to equal 2.7 times 10 to the minus fourth. Square root of both sides gives us the concentration of 0.0164 molar for our concentration of hydroxide as well as our concentration of the ammonium ion. We can use that value to find our pH by first determining what our pOH is. pOH is equal to the negative log of the concentration of hydroxide. So the negative log of 0.016 tells us that we have a pOH of 1.78. So 14 minus 1.78 will give us our pH of 12.2. And again, you could have skipped writing the whole out reaction. You could have just been like, it's gonna make some hydroxide and some cation and run with it. You would have came out with the same answer. Now, if you have a mixture of acids, you come up with a common ion problem because two acids are not going to dissociate equally. In a mixture of nitric acid and oxalic acid, nitric acid is going to dissociate first. The hydrogen has an extreme attraction for the water and will leave the nitrate ion much more readily. This is represented by the fact that nitric acid has a Ka that is massive. Oxalic acid, on the other hand, has a Ka that's itty bitty. And so it does not dissociate completely. It sets up an equilibrium where oxalic acid will make bioxalate and a hydrogen ion. Since this reaction is more heavily favored, it's more thermodynamically favorable, this reaction will happen first. And anything left over will occur with the oxalic acid. We end up with a common ion. And therefore, we have two rice tables, where the first one is pretty straightforward. Whatever this concentration is, that's the concentration of hydrogen ions we start with. This value, on the other hand, the concentration of the weak acid's hydrogen ions, is going to shift heavily in the reverse. And our concentration of hydrogen ions here is going to be near negligible. But we do need to calculate it. So, let's see one of these in actions. I have two weak acids. I've got hydrocyanuric acid and nitrous acid. We need to determine the concentration of the cyanide ion in solution. Both of these acids are going to dissociate, but notice that nitric acid's Ka is substantially larger than the Ka of hydrocyanuric acid. This means that nitric acid will dissociate first, and anything left over, hydrocyanuric acid can play with. So, we first have to set this up to determine how much hydrogen ions our nitrous acid gives up. So you'll set up your rice table like so. Now that Ka would be the concentration of the hydrogens times the concentration of the nitrous ion over the concentration of the acid, or x times x over 5 minus x. That has to equal 4 times 10 to the minus fourth. Again, this x is so small we can neglect it. So we end up with x squared over 5 has to equal 4 times 10 to the minus fourth. Multiply by 5 on both sides. I get 20 times 10 to the minus fourth equals x squared. Square root of both sides will tell me the concentration of hydrogen here, which is 0.0447. Now that's the concentration of hydrogen. It's also the concentration of the nitrate ion. So if this question was really extra, they might ask, what's the concentration of everybody? Well, the concentration of the nitrate ion is 0.0447. This question doesn't ask that, but I just want to keep a record of it. Just want to remember it. Just might not be a bad thing to do. Let's press on. Now this happens at the same time that the hydrocyanuric acid is dissociating. Hydrocyanuric acid is going to dissociate into hydrogen ions and the cyanide anion, which has an initial concentration of 1. However, here's where it's different. The initial concentration of the hydrogen ion is not 0, it's 0.0447, taken from that nitrous acid dissociating, because it's going to dissociate first. And we'll start initially with no cyanide in solution. So while this decreases by some value and this increases by that value, at equilibrium you would have something like this. And our math woes just are beginning, because remember, the Ka for cyanidic acid is going to be the concentration of the hydronium times the cyanide anion over the concentration of hydrocyanidic acid. So at equilibrium, we have our cyanide concentration times the concentration of our acid, including our common ion effect, over the initial concentration minus the change. That has to equal 6.2 times 10 to the minus 10th. Again, as long as Ka times 100 is less than the initial concentration, we can negate this X. You can also neglect this one. But Professor, the Ka doesn't relate to this. That's true. But even if X was this value, could that make a difference? If I add 6 with 9 zeros in front of it to this value, am I going to end up with anything sizably different? So I'm actually going to take the easy way out and neglect both of these x's and simplify this problem drastically. 6.2 times 10 to the minus 10th is going to equal our concentration of the hydrogen ion times the concentration of the cyanide ion over 1. In which case we multiply by 1 on both sides. Multiply by 1 on both sides, that's obviously the same value. And then divide by 0.0447 on both sides. To find that x equals 1.39 times 10 to the minus 8th. Now that value is the concentration of the cyanide ion. So, we know the concentration of the cyanide ion. We know the concentration of the nitride ion. And we could determine the concentration of the hydrogen ion, which from our Rice table we said was 0.04 plus our change, which we now know is 1.39 times 10 to the negative 8th, which in all honesty means it's the same value. Lastly, if we know how many ions are produced, we can calculate what's known as percent dissociation. Keep in mind that for weak acids, percent dissociation is going to be some insignificantly small percentage, because that's the definition of a weak acid. We can talk about them in terms of their percent dissociation by a simple percentage. What is the concentration of the hydrogen ions at equilibrium over the concentration of the acid? How much of it dissociated? So, fairly straightforward. Find the percent dissociation of acetic acid in 1 molar and 0.1 molar solutions. So, we'll set up our Rice table. If we start with 1 molar, 0 and 0, change tells us that they'll increase and decrease by some amount, so 1 minus x and x is our equilibrium concentrations. Our Ka has to equal the concentration of the hydrogen ion times the anion over the concentration of the acid at equilibrium. So x times x over 1 minus x, which would equal 1.8 times 10 to the minus 5th. Has to equal x squared over 1 minus x. Again, we can always negate this denominating x. So 1.8 times 10 to the minus 5th times 1 on both sides to cancel it out gives us x squared. So the value of x comes out to be 0.00424. Now that is the concentration of our hydrogen ions and the concentration of the acetate anion, if anyone was curious, but we can use that to determine the percent dissociation. Percent dissociation is going to be the concentration of the acid over the concentration of the hydrogen ion times 100. 0.0424 divided by 1 molar times 100 gives us that this is 0.424% dissociated. Let's compare that to 0.1 molar. In 0.1 molar, a lot of the values here are going to stay the same, with the initial concentration starting at 0.1. So we have 0.1 minus x as our denominator for our Ka expression. So Ka remains the same. 1.8 times 10 to the minus 5th has to equal x squared over 0.1 minus x. Will negate that minus x into the denominator to give us 1.8 times 10 to the minus 6 has to equal x squared. The square root of 1.8 times 10 to the minus 6 is 0.00134. Now that's the concentration of the hydrogen ions and the acetate anion in 0.1 molar acetic acid. So, plugging those values in for our percent dissociation, the concentration of the acid this time is 0.1. The concentration of the hydrogen ions is 0.0013. Our percent dissociation comes out to be 1.34%. The reason that the more dilute acid has a higher percent dissociation is because this percent dissociation is based off of the concentration of the hydrogen ion, which is related to that value of Ka, which is constant. So as the acid becomes less concentrated, that denominator decreases, while the numerator should be relatively the same since it is proportional to Ka, which is a constant for both the concentrated and the dilute. Long story short, as an acid becomes less concentrated, its percent dissociation generally increases. With that being said, You're able to do pages 18 to 21 in your packet. I will see you next time when we talk about hydrolysis.